another important aspect of linear phase FIR filters. We are going to look at constrained zeros of linear phase FIR filters. So, h of z is n going from 0 to cap n minus 1, each of n z to the minus n. So, this is the z transform of an FIR filter, general case. Now, we are going to examine two specific points in the z plane, and then we are going to see whether no matter what h of n is, are zeros present at these 2 points. And the points we are going to look at are z equal to 1. So, n going from 0 to cap n minus 1 h of n, you put z equal to 1, this is what you get. The other point that we are going to look at is h of minus 1. So, this is n going from 0 to cap n minus 1 h of n minus 1 to the minus n, which is the same as n going from 0 to n minus 1 cap n minus 1 h of n minus 1 to the minus n is the same as minus 1 to the n. So, we are going to examine the z transform of the linear phase FIR filter and look at the z transform at z equal to 1 and z equal to minus 1. To see whether there is a 0 at z equal to 1, all you need to do is you need to sum up these samples, that is what this says, right. Sum up h of n and examine whether h of 1 is 0 independent of the values of h of n, whether the z transform cap h of 1 is 0 always, no matter what h of n is. The other location is at z equal to minus 1. Rather than summing up h of n itself, you multiply by minus 1 to the n and then sum up the coefficients, the resulting sequence, and then see whether the resulting number is always 0. If it is, then you can make the statement that there is a constrained 0 either at z equal to 1 or z equal to minus 1, depending upon whether each of these statements is true or not. So, we will get a feel for this by looking at simple examples, and then the generalization will very easily follow. So, we are going to look at types 1, 2, 3 and 4 in that order, and if you recall, type 1 is even symmetry and odd length. Therefore, so this is clearly a type 1 filter. The symmetry is even and the length is odd. You have 0 to 4, 5 samples, so therefore length is odd. Therefore, to look at whether h of 1, cap h of 1 is 0 always, you need to sum up all these samples. Therefore, you add up all these things, and then you want to ask this question, is h of 1 0 always, and the other question is h of minus 1 is zero always. So, these are the two things we want to answer. So, clearly if you add up all the sequence, will you always get 0? No. Therefore, for type 1 this is not the case that h of 1 is 0 always. Now, the other thing is we have to examine at h of minus 1. So, you need to multiply by minus 1 to the n first. Therefore, this is plus minus plus minus plus. If you now look at these samples, for example, this sample corresponds, counterpart is this. After multiplying by minus 1 to the n, in this particular case they maintain the same sign, And if you look at this, this gets multiplied by minus 1, this gets multiplied by minus 1, right. Of course, this gets multiplied by plus in this particular case. Now, if you add them up, is it the case that this will always be 0? No. All right. Now, let us look at type 2. Type 2 is even symmetry as type 1, but the length is even. Therefore, so this is a simple example of a type 2 filter, even symmetry, even length. And now, if you add up all these samples, it is not in general true that this will always be 0 independent of the values of h of n. Therefore, there is no constraint 0 at z equal to 1. Now, let us look at the other thing. Now, you have plus minus plus minus. Now, if you look at this, this is multiplied by plus 1, its counterpart is getting multiplied by minus 1, and therefore, if you add them up, these two terms will cancel. Similarly, this and this now have opposite signs, and you add them up, they will cancel. Therefore, independent of h of n, for the type 2 case, cap h of minus 1 will always be 0, right. Therefore, you are forced to have a 0 at z equal to minus 1. And one immediate implication of this is, if there is a 0 at z equal to minus 1, you are guaranteed that in the z transform, it will have a factor 1 plus z inverse. That is what this means, right. Now, let us along these lines quick, we will be able to see what is going on here. Now, we are looking at type 3. Type 3 is odd symmetry and odd length. Therefore, if the first sample is 0, the last sample has to be like this. If this is like this will be like this, 2 and 3. Center sample of course is 0 because of the odd symmetry. Now, you are going to sum up all the samples. If you sum up all the samples, will they be 0? Yes, because this after all is odd symmetric, and if you sum up all the samples of an odd symmetric finite duration sequence, you are guaranteed to get 0. And now, the other possibility is you have to multiply by minus 1 to the n. Again, if you look at this, this and this, after multiplying by minus 1 to the n, continue to be having opposite signs, so they will cancel. So, this gets multiplied by minus 1, its counterpart also gets multiplied by minus 1, again they have opposite signs, they will add up to give you 0. Center sample of course is 0. Therefore, you are able to see that h of minus 1, is it always 0 for this case? Yes. Therefore, for type 3 you have constrained the zeros both at z equal to plus 1 and z equal to minus 1, and immediately you can see that 1 plus z inverse times 1 minus z inverse will be a factor of h of z. And the last case of course is type 4. So, if this were the 0th index sample, this has to be like this. So, this is 0, 1, 2, 3. Type 4 is odd symmetry, even length. Now, if you sum up all the samples, will the result always be 0? Yes. And now, let us look at the last possibility. So, this is plus minus plus minus. Now, let us look at this sample, it is now plus after multiplying by minus 1 to the n, its counterpart has now changed sign because it is getting multiplied by minus. Therefore, this and after multiplication by minus 1 to the n, these two will not cancel. Similarly here, so this is minus and this is plus, right. When you multiply by minus 1 to the n and then add them up, this changes sign and therefore, these two will not cancel. And hence, you can conclude that each of minus 1 is not always 0 for type 4. So, in the z plane, so this is 1, 2, 3 and 4. So, type 1 there is no constraint 0 either at z equal to 1 or minus 1, whereas for type 2 there is always a 0 at minus 1. For type 3 you have zeros both at z equal to 1 and z equal to minus 1, and type 4 you have a 0 at z equal to 1. So, no matter what the coefficients are, you are guaranteed that these zeros will be present given the nature of symmetry of these sequences. Now, one implication of this is that suppose you want to design say a high pass filter, can you use type 2 filter is the question, and the answer is you cannot, because for a canonical high pass filter the gain at pi must be 1, whereas here the frequency response is forced to go to 0 at omega equal to pi or z equal to minus 1, and hence this cannot be used as a high pass filter. Similarly, types 3 and 4 cannot be used for low pass, because for low pass the canonical low pass filter the gain at omega equal to 0 has to be 1, but the frequency response is forced to go to 0 at omega equal to 0 in for type 3 and type 4. In addition, type 3 cannot be used for a high pass filter, because there is a 0 at z equal to minus 1 or omega equal to pi. Therefore, the presence of these zeros kind of restrict certain kind of filters from being designed.